то очень большие нулевые когмологии. Поэтому не может быть. Они все равно нулю или минус единице. Но если равно нулю, то получается одномерное сечение, здесь одномерное. Поэтому ровно одно из них равно нулю. А все остальные будут от минус единицы, которые не носят вклад ни в нулевые, ни в первые когмологии.
Но они должны быть обязательно от минус единицы.
Да, потому что это расслоение, которое не имеет ни нулевых, ни первых когмологий. Все остальные используют там либо нулевые, либо первые.
Ну, это мы из ранга вот этого расслоения.
Из ранга мы знаем, что есть p слагаемых, да. А какие слагаемые, мы знаем из его когмологий.
Они не могут все быть О.
Могут, тогда когмологии будут, нулевые сечения будут p-мерные, а у нас нулевые сечения одномерные. Так что мы начинаем, да? Спасибо. Здоровья. Алтан, интересно, опять уехал, что ли? Вроде еще рановато. Хорошо. So, as I promised, I will not repeat any notation whatsoever, but instead we start discussing Bott, Samuelson, de Mazur, Hansen, resolutions of Schubert varieties. So there was, they were independently discovered many times. First by Bott Samuelson, but then rediscovered by de Mazur, and also before this by Hansen. So many people worked on this. And as you remember, there are Schubert varieties, XW, just the closures of certain B orbits. Or say, you take double B coset in the group and then take it quotient out modulo B and obtain some Schubert's or Breuer cell in the flag variety. And it's isomorphic to really a cell, defined space of dimensional length of W. But it has the closure, the union of this cell and some smaller cells. Yeah, W is an element of the Weil group, and in case our group is, say, SLN or GLN, then W is the symmetry group SN. These varieties are typically singular. So our resolution will depend, it will be denoted S underline. So here S underline will be reduced, so minimal length expression W equals SI1, so on, SIL, the length of W. So there are many such expressions in principle. Yeah? For example, if we have S3, then there is the longest element of length 3. Yeah? By the way, the length is, by this observation, the length is the same as the dimension of the corresponding Schubert cell, and the length of the maximal element is the dimension of the whole flag variety. So this W naught will be S1, S2, S1. Yeah, there are simple reflections. So Si is the transposition of I and I plus 1. Okay, so I hope you know this, right? But maybe we'll consider some next example. In S4, the maximal length element will be, maybe you know, there are many expressions. I started saying that it's non-unique. For example, it's S2, S1, S2 as well. Okay, so there are two different expressions for the same element. Okay, but maybe for S4, somebody knows any expression at all for the longest element. There are many, but maybe you know any at all. For example, S1, S2, S3, S1, S2, S1. This is one. It's of length 6. Okay. What I wanted to say that this is the resolution of XW. Okay, it will be called theta S. For example, if W is the longest element, so I say that this is singular in general, or may be singular, but this is always non-singular, smooth, and it's a resolution of singularities. So it's birational isomorphism. But in case when W is the longest element, the corresponding Schubert variety is the whole of flag variety, and it's non-singular by itself. There is no need to resolve it. And still, it will be very useful. For example, we will prove the Frobenius splitting of the flag variety using exactly this resolution, which is redundant. It's not needed. Yes? Yes?
Variety is in general reducible variety, yes? Or not?
Irreducible, because
Irreducible.
the group is connected, irreducible, and it's a quotient of our group, so it's reducible as well. Yeah?
And what resolution of singularities is the same as called desingularization.
Right, absolutely, absolutely.
And it is mean just birational.
Morphism from a non-singular variety. Generically one-to-one.
А почему, когда не будет сингулярности, мы все равно будем лучше пользоваться за...
We'll see this later on today, but there is a notion of embedded resolution of singularities. So the flag variety is the union of CW, of those Schubert cells, over all elements of the Weil group. And in particular, so there is this open part, CW naught, the open cell. But there are a few cells like CW naught S1 and so on, CW naught S whatever is n-1, for example. So these are divisors. Or maybe if I write X and so on, X, these are Schubert divisors. Okay, these divisors are already singular in general. And even if they're not singular, they intersect non-transversely. Say for SL3, they intersect not in a very good manner. If you take the union of those guys, this will be just one reducible divisor, something like this. But if you take its preimage in the Bott-Samuelson, De Mazur-Hansen resolution, this preimage will be already a smooth divisor with normal crossings. So the variety itself needs not to be resolved, but the variety with Schubert divisor is singular and needs to be resolved and can be resolved this way. Okay? And in general, the preimages of all Schubert varieties, as many as you have, will be just partial intersections of those smooth normal crossing divisors. Okay, so we will discuss this later on, but it's just the best possible resolution of singularities. So all the Schubert varieties are resolved simultaneously.
If a variety is a normal crossing, it is not smooth. Yes.
So once again, I say that I have such a morphism. I take some expression for the longest element. I take this morphism, theta. And then inside I take any Schubert subvariety, and I take its preimage. For example, if I take Schubert subvarieties of codimension 1, the Schubert divisors, then their preimages will be smooth divisors in here. And the preimage of anything else will be just some partial intersection of those smooth normal crossing divisors components. Okay, so it's simultaneous resolution of the whole Schubert picture, so to say. Okay, so let me give an example. Of Z, so let me say 1, 2, 3, 1, 2, 1 for the flag variety of SL4. The flag variety of SL4 are just complete flags in four-dimensional space, right? And we start with some standard flag, like K, well, 0 in K, in K2, in K3, and this is our total space, or maybe, let me not try to save space, K inside K2, inside K3, inside K4, that is our four-dimensional space V. Okay, this is just one particular point. I chose one particular standard flag, okay, and it's just one point in the flag variety. So this whole collection is just one point, the standard point, say B0, in the flag variety. Just one flag, one particular flag. And now I start moving it. So first I move it in the first place. So I write here V1, and it's one-dimensional, and this lower index 1 symbolizes that it's the first step. And then everything else is just as before. Okay, now I have to move it at the second place. So it is fixed at the first place, but here I take arbitrary. It's just arbitrary line inside this plane. So if you take the projection from all those guys to all those guys, it's just P1 fibration. In fact, this whole thing is just P1. It's the set of lines in this plane. Okay. Now this plane, for a fixed plane, for a fixed line like this, at the second step, I start deforming the second plane, but between the fixed three-dimensional space and this particular line. So this quotient is two-dimensional, and in this two-dimensional subquotient, I move the middle space, and again, it's a projection with fiber P1, right? Because above every particular V1, I have only P1 worth of those planes, right? Yes? I hope it's clear. Okay, so I start moving now at the third place.
Moving means
it means I allow it to be arbitrary, say three plane containing this two plane. Okay, now, this is fixed, but now my three plane is arbitrary, and again it's P1 fibration, and now my V1 is not standard, V2 is not standard, V3 is not standard, but remember that V1 was supposed to be contained in K2. So it's not absolutely general, right? This line, it did not change since the first step, And at the first step, it was chosen inside the standard plane. So at this point, the line is still in this two plane. So it's not most general. But I wanted to obtain arbitrary flags in the end. So I need to do something else. And now I change it again at the first place. So I write V4 because of the fourth. Oh, maybe I should, I don't know. Maybe I should keep better track of lower indices, but when nothing changes, I still write it this way. Okay, so it's still in V2, 2, it's still in V3, 3, and it's still in the total four-dimensional space. Again, it's just P1 vibration. And now I alter my flag at the second place. So I keep this line. And at the fifth step, I alter the two plane inside this 3 space. Okay, and now the sixth step is the last one.
А изначально прямая она может как пересекать его один, так может не пересекать его.
What? This one? This was chosen in arbitrary way. In particular, it could equal the standard line. Okay, so now the last step, I again modify the first one. So it's like this. V3, 3.
Modifying three-dimensional space now.
Why don't I modify it? Because it's prescribed in my sequence. I chose some sequence, 1, 2, 3, 1, 2, 1. I could choose some other one, but I chose this one. And then it shows me which subspace I should modify. First one at the first step, second one at the second step, third one at the third step, again first one at the fourth step, second one at the fifth step, again first one at the sixth, last step. Okay? That's the rule.
But these indices correspond to the reflection.
Yes.
In which sense? Say, first.
Well, I just said how I choose the simple reflections in the symmetric group, but also it corresponds to the positions of space in the flag. The first, second, third, nothing else. So in a sense, this corresponds to S1, this to S2, and this to S3.
Permutation 1, 2.
Yes, it is. And so what? Just that it happens so that the same natural numbers number many different things. For example, they number the generators of the symmetric group, but also they number the positions in the flag, in the complete flag. And it's clear that it's bijective. Okay, so now what I claim is that arbitrary complete flag can be obtained this way. And moreover, for a general complete flag, there is only unique way to obtain it this way. So namely, if this flag is in general position with respect to the standard one, yeah? So I hope in some sense it is clear what it means to be in general position. It means that the dimensions of intersections are all minimal, so to say. So we started with the most non-general flag, but what we end with is eventually most general flag. So, I mean, this line is not contained in this three space, this generality. Now, this plane is transversal to this plane. And this three space does not contain this line. Yeah? Yeah, that's the generality. And so I say, if you choose some general flag in general position with respect to the standard one, then all those intermediate guys are reconstructed uniquely, just as appropriate intersections, in fact. Okay. So we have this tower of P1 fibrations, 6 altogether, and the end thing is you just take those 3 spaces and you obtain the projection from this to the set of flags. And this is the resolution of singularities. So over the open Schubert cell, it's an isomorphism. Okay, this is the construction for GLN. And now I will formulate it in some abstract combinatorial terms for arbitrary group. But if you have any question, then please go ahead.
What is the source of this map?
All such collections. So you consider all such matrices of flags, so to say. And I say that at each...
We are interested in the last step.
The projection to flags is just taking the last flag, yes. This is the image of projection to the flags. You forget all the intermediate steps. You only remember the last step. That's your projection.
And we have
Yeah.
many sequences like this. And
Yes, well, you will have many different resolutions of singularities.
each gives a map to B.
Well, it depends. If you consider the sequences that give you reduced decomposition of the longest element, then you will have some resolution of singularities of B. But you may take some smaller sequence, for example, 1, 2, 3. Then this will be a resolution of singularities of particular Schubert variety. Well, in fact, the product S1 times S2 times S3 is so-called Coxeter element. This is the long cycle. And you will, in fact, it's also smooth. But you will obtain some fake resolution of singularities of this smooth Coxeter Schubert variety. But for SL4, there are some genuinely singular Schubert varieties, and this way you will obtain their resolution of singularities.
Why is a resolution?
Just because it's constructed as a tower of P1 fibrations. So the first one is just P1, second is some Hirzebruch surface, P1 bundle over P1, second is P1, 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 so it's definitely smooth by the very construction. Okay? But this projection is not smooth. The total space is smooth, but the last projection, forgetting all the previous rows, is not smooth. It's a resolution of singularities. Birational morphism from something smooth to some Schubert variety. Okay? So let's move on. So I will give some abstract general definition, and in the case of SLN, it will just reduce to what we did, but it may look intimidating at the first glance. So it was just some sequence of letters.
Можно уточнить?
Yes.
У нас пока флаги все полные.
Absolutely, yes, yes. But well, if you're interested in incomplete flags like this, and if you have some Schubert variety in here, then you just take its pre-image. Well, I don't know how to denote it, W prime, in here, and then you may take. So this will be just some vibration with the P mod B fibers. Okay, and so if you resolve this Schubert variety, it is in a sense enough. Well, later on we'll derive some conclusions from existence of Bose-Samuelson resolutions. Okay, but essentially I mean that all singularities in partial flag varieties, they are a particular case of singularities in the full flag variety. So there is no new problem.
То есть
If we know how to resolve all Schubert varieties in the complete flags, then we know how to do this for partial flags.
Оно вложено в многородие?
No, no, no,
Или
no,
наоборот, селективно?
no. Here it is. There is a projection like this. It's a vibration with fibers P mod B. But it's a smooth, as you see, smooth vibration. So given any singularity here, you just take full pre-image and you have, so to say, equisingular Schubert variety in the full flags. Like, for example, you can consider Grassmannian 2-4 and this flag variety, complete flag variety, projects onto Grassmannian 2-4. And inside here you have some Schubert divisor, for example, three-dimensional and singular. Yeah? And you take its pre-image, and its pre-image will be singular Schubert variety in the complete flag variety. It will be, you just remove 3 from here. No, sorry, not 3, but 2. You remove 1, 2. So you are left with 1, 3, 1, 2. It's not good because they're sorry. I'm sorry, I cannot remove 2 easily from this expression. Okay, sorry, I cannot. Yeah, maybe I'm unable to say. No, I'm able. So I want to multiply by 2. So 1, 2, 3, 1, 2, 1. I multiply by 2, and then 2, 1, 2. I write as 1, 2, 3, 1, 1, 2, 1, and then I cancel this out, and I get 1, 2, 3, 2, 1. Yeah. So this one will be singular. So this 5-dimensional Schubert divisor in the full flag variety will be singular.
Почему?
Yeah.
Пропустил момент. Почему это будет сингулярно?
Because it's equisingular. Well, I don't know your background. If you know that the Schubert divisor in the Grassmannian 2-4 is singular, then it's clear. But maybe you don't know that this Schubert variety is singular. Okay. So let me now give some general combinatorics. So given a sequence S underline, Si1 and so on, Sin, maybe let me assume that it's reduced expression for W. So I mean, this product is W. But in fact, for the construction of Bode-Samuelson variety, it's not necessary to assume that it's a reduced expression. For example, you could take S1, 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 and so on. Just then the projection to the flag variety will be not birational. It will have very big fibers. But the variety itself makes perfect sense. So I define this Bode-Samuelson variety as the following quotient, modulo the nth power of Borel subgroup. And this is just the product of parabolic subgroups in this, the minimal parabolic subgroups in this order. So this is P I1 times P I n modulo B to the power n, and P I whatever L is just the minimal parabolic subgroup So for SLN, it's just Borel was everything on diagonal and above, and here you add some element, just one element below, at lth place. Okay, so that so PIL is generated by B and some U minus alpha L. Well, alpha IL. You add just one simple negative root for generator. Okay. So by definition, there is a projection from this product of parabolic subgroups to the Bott-Samuelson resolution. It's called pi s, and we consider the following diagram. So I have pi s, sorry, ps projects by pi s to the Bott-Samuelson resolution. Now it embeds into the nth power of the flag variety, and this thing embeds into the nth power of our group. And there is an evident projection here, just because the flag variety is the homogeneous space of G. And now, what is phi n? Maybe I'll know all of the phi s also. So phi n is a map from nth power of my group to itself, and it works like this. G1 and so on. Gn goes to some partial products. So it goes to G1, and then G1, G2, and then so on, and then G1, G2, Gn minus 1, Gn. Yes.
В предыдущем примере увидеть вот этот,
Yes.
вот этот фактор по параболическим вот этим группам. Что будет являться вот здесь?
So when I take this minimal parabolic subgroup, then when I take the quotient PIL modulo Borel, it's just projective line. You see, they differ just in some one-dimensional piece, and this project, this quotient is just P1. Okay, so these P1s in all these fibrations are just quotients of various parabolic subgroups modulo. So yeah, when I fix all the parts of flag just except for one, say at this point, the new one will be that, yeah. Before it was that, before that, before that, then it will be this, and then, okay. So each one of them moves inside P1, and this P1 is just the quotient of the corresponding parabolic modulo Borel. So that's what is formally written here. Phi n is a map from the product of the group to itself, and the product of this group contains the product of parabolic subgroups. So it's just a restriction to the product of parabolic subgroups. Okay, what else do we have to define? The lower phi s from P1 and so on, Pn equals P1, B, P1, P2, B, and so on, P1, P2, Pn minus 1, Pn, B. B is the standard Borel subgroup, the upper triangular Borel subgroup. Okay, so this diagram is clearly clearly Cartesian, and so it follows that, for example, this is smooth, right? Because this map is smooth, and this map is smooth, and the product of parabolics is smooth. So this is smooth, this is smooth, and hence this is also smooth. Okay. So we can project to the last factor here, and we obtain this morphism theta s, and this is the last factor. So in this, I keep track of all the possible flags in the intermediate steps, right? This map embedding into the product of flag varieties is just when I remember all the rows, okay? But when I forget all the rows except for the last one, it is my resolution of singularities map theta. What else do we need? Maybe the action of the first parabolic subgroup. So the left multiplication by p I1 equals it with the action of pi1 on the whole resolution. Okay. For each parabolic subgroup, we have Schubert decomposition, so to say. It has exactly for minimal parabolic subgroup, it's the union of exactly two double cosets, namely B and BSI B. Yeah, like in here, and it corresponds to decomposition of P1 into two cells, point and the affine line. Here we know that if we take just the unipotent subgroup, one-dimensional, as depicted there, and multiply it with B, we get BSI B. Maybe I should write minus alpha. Okay. Then it means that inside the Bott-Samuelson variety, you have an open part, ZS open. So it's the union of BSI1 B times so on times BSIN B modulo B to the n. I explained that this is a resolution of singularities, that on this open part, the projection theta S in an isomorphism to the Schubert cell CW. Yeah, because each of these quotients is just a fine line, and altogether you obtain the fine line to the power length of W. This is n. Okay, so this is not S. This is an isomorphism. Okay, what else do we need? So now I will erase this beautiful illustration. But now I will explain that one particular Bode-Simonson resolution, for example, the one I'm erasing, contains in it all the smaller resolutions as subvarieties. So for a subsequence like J, so I had this reduced sequence I1 and so on, IN, and here this will be the sequence 1, J1, so on, Jm. So I just pick out some of those simple reflections. I forget part of them, and I pick out some of them, and we obtain a closed embedding. From the resolution given by this subsequence into the full resolution, namely if I have elements of parabolic subgroups Jm, just will go to those elements extended by ones at the missing places. 1, 1, then at some point I get Pj1, then so on, then the last Pjm, and then again ones, and some ones in the. So I just, whenever I have this, wherever I have the index of this subsequence, I put the corresponding parabolic elements. Wherever I don't, I just put ones. Okay, extend by a sequence of ones. And we will need some particular cases of this closed embedding. So for m less than n, I will have just the first interval of this sequence, S1 and S1, I1 and so on, SIM. Just I take some first interval in here, up to m. And then I obtain also, I have a closed embedding like this, but I also have projection psi SM from the Bode-Simonson resolution to the resolution like that, namely, I just take P1 and so on, Pn goes to P1 and so on, Pm. So if you remember those rows, yeah, I just forget the last rows. This is my projection. Yes, so my resolution map theta was forgetting all the rows but the last one, and this is something opposite. I forget the last few rows. Okay, and psi s is psi s n minus 1, so I forget exactly the last row. Last row. So in general, such a projection is composition of a few like this. Yeah, I forget the last row, then before last, and so on. Fine, and maybe let me set R is S of n minus 1, that is Si1, so on, Si n minus 1. I forget just the very last reflection, and then this psi will be a P1 torsor. So psi S is a P1 torsor from ZS to ZR. Okay, and then recursively ZS is a tower. Maybe I shouldn't say P1 torsor, maybe P1 fibration, I should say. A tower of P1 fibrations. Okay, that's what we discussed in this picture, that each next time I add P1 worth of flags. Okay, because I allow each new flag only modify at one particular place. And there's only P1 freedom of such choices. Okay, what else do we need? Is that this P1 fibration has a section sigma s from ZR to ZS, namely the collection of parabolic elements goes to the same collection extended by 1, just as here. It's a particular case of this general construction. And maybe I didn't stress this point at this beautiful picture, but let me stress it now. So I had this V1, sorry, say V, whatever, 4, 1, V, I think 2, 2, V, 3, 3 in K4. Yeah, and then I modified this guy. V1, 4 is the same, V5, 2 is modified, V3, 3 it is before, right? And so here my modification runs in P1, right? Because this is fixed, and in between this two-dimensional quotient, I modify one-dimensional subquotient, right? But there was an initial choice of this. Yeah, so I could make no modification, but stay with this choice. And this is my section. Yeah, so I have P1 worth of new choices, but I can just stay with the old choice. This is my section. Okay, fine. I think now we're almost introduced all the notation. What do I want to erase? maybe this. Now I will just say a few words about line bundles, and then we'll be ready to prove the Frobenius splitting for Bose-Samuelson bisingular relations.
Почему нельзя работать с исходным
Yes?
Б? Зачем его разрешать нужно?
Well, as I said, if you take arbitrary element of the Weil group and corresponding Schubert variety, then you obtain a resolution of this Schubert variety. And you probably want to resolve some Schubert varieties. But even without this, if you take the longest element and you obtain, so to say, a resolution of the whole flag variety, you will see maybe in half an hour how it's used to prove the Frobenius splitting of the whole flag variety. But first, let's prove the Frobenius splitting of Bose-Samuelson varieties. Last time we introduced the varieties L of lambda. So it's a line bundle on the flag variety. And now we have some Bose-Samuelson resolution. It goes to the Schubert variety, which is embedded into flag variety. So I have this total map, also theta, and Ls of lambda, by definition, is the pullback of this line bundle to the Bose-Samuelson variety.
А вот это L от лямбда, это то, что называлось ассоциированный вектор.
Yes. Yes. It was associated to some character of Borel subgroup. Okay. So yeah, I've just erased those closed embeddings, but I will need them right now. So there's the notion of the boundary of the Bose-Samuelson resolution is just the union from of all the divisors so S of j is obtained just by we throw away ij in this sequence, or maybe S ij. So this new sequence is not necessarily reduced, as we observed, but that doesn't matter. So it will not be a resolution of something in the flag variety, but inside Bose-Samuelson, it's just a divisor. Okay. So if I have some arbitrary subsequence, then the Sj, as we had here, is just the intersection of the S of j over all j in this subset. Okay. And this is just transversal intersection of smooth divisors. Okay, so that's what I announced before. Yeah, that inside the Bose-Samuelson resolution, those sections give rise to the smooth divisors, and these smooth divisors, if we intersect them, they give all the Bose-Samuelson sub-resolutions. Okay, so upstairs in this resolution, everything is very nice and simple. It's just transversal intersection of smooth divisors. Okay. So so now let's prove some prerequisite for Frobenius splitting. It will be proposition number 5. And it says the canonical line bundle of the Bose-Samuelson resolution is calculated like this. So it's the O twisted by the negative boundary, tensor LS of negative rho. And then also, if you want it B equivariantly, then you say it's also tensor K minus rho, and this B equivariantly. So if you don't care about B equivariance, so I said that the parabolic group PI1 acts on the Bose-Samuelson resolution. In particular, Borel acts there, and there's just some character of Borel, and if you want to keep track of it, you are welcome. Otherwise, I just say that as a line bundle, there's a product of those two. So one is pulled back from the flag variety. Another one is just O of negative boundary. Okay? This is the character of Borel. So Borel acts by the character negative rho. It's one-dimensional representation with a character negative rho. And say the simplest case is SL2, and then well, essentially there is just one thing, ZS, there's just P1. And in this P1, the boundary is just one point, right? And LS of minus rho is just O of minus 1. So you get omega P1 is O P1 of some point, say minus 0, tensor O. So I have to write O of minus 1. This is, but well, maybe let me write some point X. So there's somewhat different meanings. There's O of minus point, and there's degree minus 1 line bundle. But they're the same. So the tensor product is just O of minus 2, and we know this. Okay? And so that's generalization of this observation to arbitrary groups. Okay. What shall I raise? We will need this notation soon, but unfortunately I will destroy it. Okay, this is some nice elementary calculation, and let me start with some lemma. I mean, we will prove it inductively by the induction in the length of our sequence. Okay, so I will take, well, what I just erased. We'll take R, that is S of n minus 1. I forget the last index. Yeah, and we'll have this projection from Z S to ZR, and also we'll have a section back, as we discussed, right? And in this general setting, it will follow. So here's my general setting. I have a projection from X to Y, say psi, and also some section sigma. So it's a P1 bundle and a section. And then I say D in X is the image divisor is the image of this section, sigma of Y. So I claim that in this situation the relative canonical bundle so what does it mean? I can take the canonical bundle of X and I can take the canonical bundle of Y and I can pull back, okay, and then I can divide like this. It'll be the relative canonical line bundle. So it's sort of
Divide quotient by, you mean? We're dividing K theory, you mean?
well, these are line bundles. They're invertible, and I can tensor them in this sense. Yeah, the invertible sheaves. I can tensor them.
But in
Yes?
general, the relative canonical is
It's canonical. Yeah, I can also consider relative, for example, cotangent or tangent, and then I would have to take quotient. That's right. But for the top degree, it's just this. Okay, it's a line bundle, tensor product of two other line bundles. So in a sense, it's well, it's wrong, but roughly speaking, it's trivial along the base, but along the fibers. Well, at least restriction to any fiber is the canonical line bundle of this fiber. That's for sure. Okay, so this guy is isomorphic to OX of negative twice D tensor psi sigma pullback of O of D, OX of D. Okay. That's the first claim. Maybe let me prove it right away. So what do we know? We know that OX of minus D is the ideal sheaf of this divisor of sigma of Y. Okay, but by the very definition, maybe let me call it the ideal sheaf of divisor D, and hence the conormal bundle to this divisor is O of X of negative D restricted to D, and hence the pullback with respect to the section of the relative canonical bundle is the pullback of OX of negative D. And now it remains to just tensor with OX of 2D. And what we get is the pullback with respect to section of the relative canonical line bundle, tensor OX of 2D is the pullback of OX of D. Okay, so we proved A, and now it follows that if we are given any line bundle on X with the only information known about it, that its degree along the fibers is 1. So if degree of L to any fiber psi inverse of Y is 1, then the canonical, relative canonical line bundle is OX of negative D, tensor L inverse, tensor psi sigma pullback of L. Okay, and the proof of this is that, well, we already know the part A. And now if degree along fibers of two line bundles coincide, then the product of one line bundle with the restriction to the section is the isomorphic to the same thing for the other one. Okay, just because well, if you take the ratio of those two things, so let's just regroup the thing. It means that L1 inverse tensor L2 is the restriction of L1 inverse tensor L2, right? And you know that this thing has degree 0 along the fibers, right? Because they have the same degree. The ratio has degree 0 along the fibers. So it must be the pullback of something from the base. But how to find what is the pullback of? It's just restriction to this section. Okay. So there we are, and then because it's trivial, it's a line bundle along P1, and any line bundle of degree 0 on P1 is trivial. So it's trivial along all fibers, so it's pulled back from the base, and then from its restriction to the section on the base. Okay, so we know this lemma, and now let's apply it to our situation. In our situation, let's prove the proposition by induction in n, in the length of our sequence. So for n equals 1, we already discussed it. The base is clear. And then we just use the lemma for the inductive step. So we take the P1 bundle P1 bundle psi s from ZS to ZR, as I promised, with section sigma s. And then if we take Ls of rho and restrict it to the fiber of psi s, my PP1 bundle, then the degree is 1. Okay, because of the nature of rho. Rho was the sum of all fundamental weights.
Сейчас, а база индукция, она тривиальная, так?
Yeah, induction base we just discussed here. It's P1, or even before. You could consider P1 mapping to the point. For the point, it's absolutely nothing to discuss. Okay, so we know this for. So this is the importance of rho. That's why the rho appears here. That it gives you some line bundle of degree 1 along any P1. If we restrict sigma s of ls of rho, will be just L r of rho. I mean, it's natural, yeah? You pull everything back from the flag variety, and you have ZR embeds into ZS, and then it goes into the flag variety. So by naturality, you get this. Then, just applying this lemma, we have that omega s is the pullback of omega r tensor O of negative twice the section tensor sigma s composition with psi s O of sigma s. Okay, and that's what we want to prove. That's what we wanted to prove up to this scalar, and this scalar maybe let me leave it out. If you are interested, you can check at some particular point, say at 1. Okay. So now let us prove the Frobenius splitting of the both Samuelson variety, and this Frobenius splitting for the flag variety, for example, will follow, and not only that, but compatibly with all Schubert varieties. So something very strong. It will follow immediately, but maybe next time. And now, theorem 5 says that take a section sigma of the anti-canonical bundle vanishing at all, well, at the boundary. DZS. And we know that this exists. I mean, non-zero section vanishing at the boundary, it exists by this formula, right? Because we take anti-canonical class, then it will be O of the boundary times LS of rho, right? And now this LS of rho, rho is a dominant weight, so there are some sections on the flag variety, and we can pull back some section from the flag variety, and it will vanish along the boundary. Okay, so by this proposition, there is such a section. So it exists by proposition 5, since the global sections of the flag variety with coefficients in L of rho are non-zero, while this is some, again, basic structure thing of group theory, but maybe let me not discuss this. I mean, for any dominant weight, such sections will be non-trivial. It's in case of P1, it'll be just H0 of P1 O of K is non-zero for K non-negative. And this is similar for arbitrary groups. So we take such a section, once again, that vanish at the boundary. Then, first of all, sigma to the power p minus 1 splits the Bose-Samuelson resolution. And second, for any subsequence Sj in S, the corresponding Bose-Samuelson subresolution is split compatibly by the same sigma to the power p minus 1. Okay. So after we made all this preparation, this follows easily, immediately. So, as I said, we obtained this section just by pulling back a section from here. Okay, and there is some non-zero section. So maybe choose a non-zero section of L of rho on B carefully such that this section restricted to the particular point B in the flag variety does not vanish. Okay, it does vanish somewhere. In fact, it vanishes along, for example, we can choose such a section that vanishes along the boundary of flag variety. I mean, the zero section of zero divisor will be the union of Schubert divisors. Okay, but it is non-zero at the open Schubert cell, and we want this open Schubert cell to contain the standard point B. Okay, so this section does not vanish, and this means that our section sigma will not vanish at the point 1, 1, 1. Sigma received to the point 1, 1 does not vanish. Okay, but then, oh, sorry. No, it's not this. I'm sorry. Choose non-zero section, maybe tau, such that tau received here is not zero. And then the zero divisor of sigma will be exactly the boundary with multiplicities 1. So z, well, how to say it, the union of z s of j, j goes from 1 to n, and also union of zero divisor of tau, and we pull it back, theta S inverse. Okay? Because our section is the product of two. One is the canonical section of this, or rather of the opposite, which vanishes along all the boundary by construction. Another section of that, but we chose the pullback of this section so that it does not vanish at this particular point. And to this particular point, there goes 1, so on, 1. Okay? And so the zero divisor of the second factor is away from this particular point. So we have this normal crossing divisor of the boundary of the Bose-Samuelson resolution, and our section by definition vanishes here, but also there is some other part which is pulled back from the flag variety. But this other part we chose carefully so that does not vanish here. So the total zero divisor is just this transversal union of boundary components plus some junk somewhere far away. It doesn't matter because it's just, you can forget about it. It's just for the correct action of Borel. It doesn't matter. The line bundle by itself is just this. Okay, but then if you recall, it was called, I forgot, theorem 3 or proposition 3. Then it says that in such situation, sigma splits, sigma to the power p minus 1 splits, and compatibly with all those. So now just apply proposition 3 from the last or even before last time. Okay, so we had a section of anti-canonical bundle that was vanishing along some divisor with smooth transversal intersections and some junk away from the intersection point. Then its p minus first power splits everything compatibly with all those components of smooth normal crossing divisor. Which variety? Because we don't have such a situation on B. This nice normal crossing divisor was only available in the Bose-Samuelson resolution. There is no such thing in B. Which was, if you just read the statement of proposition 3, it is exactly what you need. You need some normal crossing divisor plus some junk far away from the crossing point. That's what we achieved.
So now we didn't prove yet that
the flag variety itself is split. I don't have time, but it's an immediate corollary. And it doesn't need any specific of the situation. So whenever you have a resolution of singularities from something split to something else, it's normal, say, normal base. Then the base is automatically split as well. Oh, well, if we plan to stop next time, then we don't need these fancy notions. But if we plan to prove this wild character formula, deduced from de Mazur character formula, then to keep de Mazur recursive, well, inductive formula going, you do need to have this extra splitting. So in particular, you do need all the Schubert varieties to be normal. And in fact, that's what was missing in the original paper of de Mazur. So he introduced those de Mazur resolutions and used them to prove de Mazur character formula in some 1973 famous paper. But then somebody noticed that he didn't prove the normality of Schubert varieties, but used it in his inductive argument. And then there came those Indian guys, and like Ramanathan and others, and they used Frobenius splitting to prove its normality, to fill in the gap of the original de Mazur paper. Yeah, absolutely, absolutely. Everything is taken from Brion Kumar. Yes, absolutely.
Просто есть какой групповой контекст.
Yes. Hmm. Yeah. And in fact, if you feel like stopping this class at any time, just feel free to tell me, and we'll stop at any time you wish. It's up to you.